All right, thank you, Jim. And I can say from personal experience that the folks at KSC are very operationally oriented, very let's get the job done oriented. So anyone who is interested in these facilities will find them to be a very willing and capable partner. My name is Jim Van Lack, for those of you who don't know me, and it's my distinct pleasure to be able to introduce someone who's not only extremely well known and well respected, but he's also a very good friend of mine. General Joe Engle has agreed to come and visit with us today and talk about his wonderful experiences in aerospace. He is retired from the Air Force, of course, and has just an absolutely astonishing career. Interestingly enough, he was one of the 12 individuals to fly the X-15. He flew it 16 times. And I was very fortunate, living and working in Houston, to have all kinds of astronauts around the house. And to be honest, the kids were not all that excited. But when I saw Joe's picture on television one day and said, "There's my good friend Joe Engle," my kids said, "Joe Engle? You know Joe Engle flew the X-15." So it's a very distinctive honor that he was able to do that. Among the other many things that he did was he flew, was the commander of one of the two crews that did the approach and landing tests, which were where the Space Shuttle Enterprise was released from the 747 and did the initial glide testing before they actually flew the Space Shuttle to orbit. And he also commanded 2 different missions of the Space Shuttle. He has flown 185 different types of aircraft, has 15,000 hours of flying airplanes and 224 hours in space, and has been inducted in numerous honors of various kinds. My own personal favorite of those is being test pilot emeritus at the Air Force Test Pilot School, so he has fantastic opportunities and fantastic recognition. So there are too many other honors to go into, but I'd like to please introduce Joe.
Thank you, Jim, and thank you all, everybody. I'm impressed, I'm honored, and I'm quite honestly, I'm humbled to get to be up here on the podium to talk to you guys and gals. And Jim has been come up. It was really put in a little different context of, hey, how about, would you like to come up and share some fine stories about the X-15? And I kind of envisioned more of a hangar wrap thing. You know, at the end of the day, where flying's all done, everybody's sitting around with a beer in their hand, and you're just exchanging stories. Hell, I haven't seen a beer in this room since I got here. Fix that next time, George. I brought toys, so I'm feeling kind of comfortable. And I've got stuff I'd like to tell you that I've realized it's going to be packed in. I'm going to talk fast. I may have to skip over some stuff. Hopefully there'll be a little bit of time at the end for questions. We got a coffee break coming up, and I'll be glad to hang around up here or out there and just shoot the bull with you, because that's where the most fun is. I've also got kind of a guideline of where I got to be time-wise in order to get done on time. So I'm gonna start out. If I can find the thing here, and plan to share this kind of stuff with you. Talk a little bit about the airplanes that preceded the X-15, the rocket research aircraft that preceded the airplane, the X-15. Describe the X-15, some of the things we learned during the heating profiles, during the heating flights, and high-speed flights, and then some of the things we learned during the altitude flights. The main thing that I'd like to walk away with here is that last add-on bullet, that can any lessons learned help you guys out. And that I added on. I realized when I got here, that's what this whole conference is about. It's not just to hear stories and old fine stories, but are there things that we've learned in programs that are similar in some ways to the kinds of things that you're either doing or thinking of doing that you could maybe pick up on and avoid some of those potholes, some of those hurdles that we ran into? The X-series airplanes were really prominent out at Edwards during the 50s and 60s. That was a great time to be at Edwards. There was just a whole batch of airplanes. Right after the war, the X-1, I got a dead pointer in my thing here that I can use. Yeah, the X-1, of course, was the first, and there were actually a batch of X-1s. There were 9 different X-1 modifications that flew out at Edwards. And X2, D558, a whole series, a whole stable, really impressive, leading up to the X15. And it all happened, started in 1947 when the X1 came out. It arrived at Edwards. Chuck grabbed it, and the object was to go faster than the speed of sound. The object really was to gather data, to build airplanes that were better, and at that time that meant faster than the bad guy said. Because at that time the theory was if you can go faster than the bad guy, you win. You're going to be able to win. We kind of learned that there's kind of a limit to that, probably around a little over Mach 2, and that's why you'll see most of our fighters are Mach 2 fighters. And then we got missiles that carry it on out as fast as you want to go, faster than the airplane can go. But the other thing that we didn't realize at the time, that we were really laying the groundwork for aircraft that would be following on. Dinosaur, Space Shuttle, and some of the aircraft that you guys are developing now. Wrong button. This all happened, as I said, between about 1947 and up through the late 60s. And chronologically, you can see where the airplane expansion program was going on. That's about in parallel with where Mercury, Gemini, and the early Apollo flights were going on. So they were a dual effort. The X1, specifically designed to study and learn about transition flight. Mach 1, as you transition in up to and started to form the shock waves and press on through Mach 1 and into low supersonic flight. The problems, of course, were that shock waves would form on the thickest part of the airfoil, and after that shock wave, the control surface would be relatively ineffective, and more ineffective as the shock got stronger. Chuck and Jack Ridley realized that if they could move the whole tailplane back here with the trim motor, the pneumatic trim motor, they could use that whole surface for pitch control. And Chuck was losing control. He was losing effectiveness in pitch with just the elevator. When they decided to try that technique, he was able to control the airplane through Mach 1. Now the X1 had 6,000 pound thrust engine. Actually, there was 4 chambers. Each one had 1,500 pounds of thrust, and they could be ignited separately. So you could have 1,500 pounds, 3,000, so on up to 6,000 pounds of thrust. I don't think you could restart those in flight, but you maybe could. I don't remember whether you could do that or not. The airplane was designed to go Mach 1. It flew up to about 72,000 feet, but altitude was not one of the objectives back then in those days. It was to go fast. They didn't really care about going high. It didn't have reaction controls. No provisions were made for flying exo-atmosphere, or where the dynamic pressure got so low, you didn't have any control. The the Douglas D558 was coming along kind of parallel with the X1. It didn't fly as early as X1, but it flew just a couple of years after X1. It was designed to go Mach 2. It used the same engine as the X1. It was a Navy, the X1 was an Air Force NASA or Air Force NACA program. The D558 was a Navy NACA program, so there was naturally that rivalry, and it was a great rivalry too. It was sometimes it got really, really healthy. And, and Scott Gillespie, of course, had the airplane that was going to go Mach 2. It was pretty. God, it was prettier than the X1. Pointy nose, swept wings, big tail. And he did. He made Mach 2. It was designed to go Mach 2. He kind of coincidentally got up to 83,000 feet instead of the 70,000 feet. But that was, again, not objective. It was the fact that he was going faster, could get up, have the same effectiveness with the controls because of dynamic pressure at a higher altitude, and less drag, so they could go faster. Well, Bell Aircraft and the Air Force and Yeager, they were just incensed that the Navy was going to hold those world speed records, so they figured how they could get the X1 to go faster than the D558-2, and the 558-2 had no fuel. It actually could take off from the runway, but it couldn't do, once it got off the ground, it couldn't do very much after that. But they decided if they could stretch fuselage, get more propellant in there, burn the engine longer, they could get it out to possibly 2.5, Mach 2.5. And that was the goal. The design goal of this airplane was 2.5. Chuck got it out to 2.44. and was at about altitude of about 90,000 feet. And as he turned, as he banked to head back to the field, after shutting the engine down, this was an envelope expansion flight. So he deliberately shut it down at 244, banked to turn back, and the adverse yaw got him, yawed the airplane out, and there was not enough directional control, directional stability with the vertical fin. The airplane swapped ends and tumbled all axes, plus and minus 9 Gs, I think, or 12 Gs, something like that. And he tumbled from 90,000 feet, recovered at 15,000, and made it back to the dry lake bed and landed the airplane okay. But they decided that's probably enough for that. The Bell X2 was designed specifically to go to Mach 3. That was the design goal of the airplane. Mel Abt, when he was flying the airplane, it had a larger engine. It had a 15,000-pound thrust engine. I think I mentioned all the X1s and the 558-2 had the LR11 engine, the four-chamber engine. This had a larger engine in it, and Mel got it out to, in the envelope expansion program again, he got it out to 2.87, shut the engine down, back to head back to Edwards. Exactly the same thing happened to Chuck. The adverse yaw got him, took the airplane out of control, and the airplane broke up, and we lost both the airplane and Mel on that flight. So the design to go Mach 3 got almost out to Mach 3. The next X-series airplane in the envelope expansion program was the X-15. Altitude, this was the first airplane that altitude was one of the design requirements, and it was designed to go to 250,000 feet. They figured they could get above sensible atmosphere, look at the problems involved with transitioning from aerodynamic surfaces to reaction controls, both exiting the atmosphere and then transitioning, coming back into the atmosphere. So the design goal was Mach 6, 250,000 feet. The airplane actually got out to 6.7 before reaching kind of what was agreed to as a limit, and you'll see why here in just a minute, and got up to 354,000 feet. Now, it was a pretty big step, pretty good step, because if you look, and don't hold me to the exact area of these performance envelopes, I just learned how to use a computer, and I can draw ellipses, but I'm limited on the shading of the stuff. But the X1 was designed to go Mach 1, and it did. It got to Mach 1, okay, a little over 70,000. D558 got out to Mach 2 successfully. 80,000 feet. The X1A got out to almost 2.5, the design goal, 90,000 feet or so, but it lost control. The X2, designed to go Mach 2, didn't quite make it to Mach 2, lost control, lost the airplane. So, you know, the next step in this envelope expansion thing was a pretty gutsy thing on those guys back then, because here we had this airplane made it okay, this airplane worked okay, this one really didn't, and this one really didn't. So I don't know what the logic was going through their mind, but they said, okay, well, let's go ahead and have an envelope that looks kind of like this. and actually, this was the design envelope. The actual 6.7 goes on out and up higher, so it was a pretty aggressive step in what are we going to do next after the X2. Especially when you figure that the technology that the guys had back then was pretty basic. A lot of folks in the room remember this slide reel thing. Punch card computers and stuff, that was really it. There was not a lot of telemetry either. A lot of the data was recorded on board, and that's what I remember. Bob Hoover came up one day, and you know, gave him this sage advice on being a good old test pilot. He said, if you get out of control and you can see you're not going to make it back to the runway, don't bail out. Fly up right into the crash site, because probably we can get more data back that way. A few things that are kind of unique. This is a good picture to see the tail, and notice that the tail is a wedge-shaped tail, pointy on the leading edge, but very, very blunt on the back, like an old John boat on the back end. The fuselage primarily was propellant. anhydrous ammonia and liquid oxygen, 2 cylindrical tanks. On either side of those cylindrical tanks, there were chimes that came out. They don't show up too good on here. Maybe maybe in the film it'll show. But those chimes housed the cables for the control surfaces going back to the tail, and hydraulic lines that went back, electronic wires that went back. Everything on this airplane was really basic. It was just cables and hydraulic actuators and stuff. The interesting thing, problem that was run into with that, I'll talk about in just a little bit. Where's my changer? Here it is. The cockpit looked pretty standard at first glance. The most airplane cockpits at that time. The flight group, the flight instrumentation was kind of in this scan pattern like this. Actually, the inertial instruments, which were used really for shutdown information, and when you really got accelerated out almost to max speed, the inertial instruments, the aerodynamic instruments, the pneumatic instruments were not good anymore, of course, either for high-speed flight or for altitude flights. So the inertial instruments were grouped in a smaller scan pattern so you could get around them real fast. But they didn't work very good because those inertial systems back then, they drifted a lot under acceleration. At launch, you had 2 Gs come on with the throttle, get the engine lit, and you'd have 2 Gs, and then as the propellant burned out, as fuel burned out, just dead burned out, the airplane only weighed 15,000 pounds, it had 60,000 pounds thrust, so you had 4 Gs pushing back. And when you saw Jeff Ashby in that film, and somebody showed it over here in the next room, so he was really surprised when he came off a G level like that to nothing. Well, that would happen when the engine shut down, or when you shut the engine down, especially on speed flights. You would be you get almost a 1 G deceleration, so there's a net of about 5 Gs difference. And of course, with a stick, we had 3 controllers in the airplane: a center stick, which was standard, and a sidearm controller, and a reaction controller. Now, these are kind of insets. It's a little confusing. Maybe that's a little better, show you where it is. But you can see the sidearm controller over here a little bit. It actually, which is like it used in a lot of airplanes now, F-16s, most airplanes, a lot of airliners, in fact, have sidearm controllers. That was designed so that it rotated about your wrist, so that in that G transition, you'd get a forward and aft motion, but it didn't translate into a stick input, because that's the last time in the world you want to make, a big stick input is when you're at Mach 6, and just like any airplane, you're going real fast, and the dynamic pressure builds up, and the airplane just tightens up. It gets more and more sensitive, just gets tighter in the damn drum. And you feel like you're milking a mouse. You just want to don't know how to do anything big about it. And then the other thing that's kind of interesting is that the airplane had spots in it. The airplane that would grow. As it heated up, it would grow in length, about 3.5 inches. It was 50 feet long, and it would grow 3.5 inches. And they had slots, expansion slots like bridges have. They'll come together like that. You can go to look at the airplane in the museum over there. Back here along the chines, you can see these slots about every 18 inches with little pins and holes, and the metal comes together. But there isn't any around the fuselage because the boundary layer would lay too close, and they're afraid that the boundary layer would peel the skin up. So the boundary layer just acted like an old oil can out in the garage. And, you set it out in the driveway, and it expanded and pop and bang. And that's 1/4-inch steel up there. So, God, when you're right there, when you're milking that mouse, and you don't want to do anything big, somebody had hit the side of that thing with a sledgehammer, and it'd just go ka-bam! And boy, that was all you could do to keep going. What the hell happened? The landing gear handle, everything was really, really simple on this airplane. Not only cables going to actuators and stuff like that, no autopilot, no attitude hold or anything. But the landing gear was very simple. It was a T-handle, like an emergency gear on a lot of airplanes. A T-handle that you just pulled, and that cable went over a pulley and down the bell cranks, and the gear was held with just mechanical hooks. So you jerked on that cable, you pulled the hook out, and the gear fell down by gravity and into the airstream and came down. and that kind of got to us, and we got shut. I hope I covered that. Let me see, getting back here, the cockpit, flight instruments, propellant instruments, the pressurization and pumps for propellant. This was for APUs, the auxiliary power units. We had 2 of them for redundancy. And I think the throttle over here is about it. Then getting into the flight instruments, these are the inertial instruments which, as I said, really didn't work too good. So for shutdown conditions, to make sure we shut down on the right energy, we used a stopwatch. And the stopwatch, the engines were had an ablative coating on the inside of them, and I think about every 6 flights they had to be sent back to Thiokol and recoated, and that would give them a little bit different thrust. So the new engine would come in and mount it on the airplane, and you'd take it out to the thrust stand, bolt it down the thrust stand, run it up to 100%, measure the thrust, and then the engineers would take that thrust and compute how many seconds of burn time you wanted in order to shut down the conditions that they wanted for that particular flight, for the data for that flight. And that stopwatch was activated on chamber pressure, and then it would shut down if the chamber pressure ever dropped. So if you got a light and you burned for 12 seconds and it shut down, you didn't have to say, holy crap, how long has this thing been burning? You'd look up there and you'd see 12 seconds and you know what lake bed, what dry lake bed you needed to head to right away to go in for an emergency landing. I want to mention a few things on this here. You can see the wedge tail again. What the deal was on that, directional control, directional stability was a real problem on all the other airplanes, all the other X airplanes, as you got higher and higher Mach numbers. And at the hypersonic speeds, the airflow actually is separated by this wedge, and it can't come right back together again. It takes a while. You know, like on a boat, if you get going real fast on a motorboat and you look back behind you, it takes a while for the water to get back together, but it does. And the same thing happens with the free airstream on a wedge airplane, a wedge tail like that. It would come out and it would almost double the effective size of the vertical fin, which essentially gave you twice the stability without paying the penalty for the weight and the structure. So it was a very clever thing. Now, subsonic, when you came into land, it gave you a lot of drag. There was a lot of turbulence back there, but you really didn't care then because you had plenty, you had a good enough LRD, you could afford that extra drag. It didn't bother you at that point in time. The landing gear, get the right hand here. The landing gear was somewhat unique too. It had skids, steel skids that folded up forward up against the fuselage and were held in place with these locks, these mechanical locks. The nose gear, the only rubber we had on the airplane was the nose wheel tires, and that was to cut down drag up front. It was not steerable, it was a full caster nose wheel, and it would fold forward as well with the same hook from the cable up here on the instrument panel came down to the bell crank, went forward and aft, and you just mechanically unhooked the gear and it would fall down. We landed on a lake bed. The airplane was designed to land on a lake bed, so directional stability, or directional control, was not really one of the objectives of the landing gear system. Its stability was to make sure that it didn't ground loop or go out of control. So you put all the drag back here at the tail end of the airplane and made it a very stable airplane. In fact, if it started to drift off to one side or the other, you could load up the skid with ailerons from touchdown, about 200 knots, down to about 100 knots, and then it was not effective anymore. You could kind of make it think like it was going to go back, but it was more like the little cars, you know, at the carnival that have the steering wheel, but that doesn't do anything. But you're on a lake bed, so you really didn't care. I mean, it was 8.5 miles wide, so you weren't going to get to the edge of it anyway, even if you wanted. In the film that I've got, you're going to be seeing quite a few photos, looking back at the tail, seeing the tail group here. Those cameras are located right in these little bumps right here. They're called bug-eye cameras, and there's one on each side. And that was used partly for data collection, mainly for data collection as well. Let's see, I can't think of anything else on this one. Oh, the landing gear. Yeah, the landing gear gave a lot of stability on the ground. That was a good deal. But it was really a menace, because when you touch down, when the main gear touched down, that nose was going to fall through and just slam. And it really hit hard. It really did hit hard. It was ugly. You knew it was going to be ugly. When you touched it, you could get, every pilot likes to have a nice, smooth, trickle-on touchdown, you know, and then ease the nose down, and it looked like you know what you're doing, and look over and grin at the crowd. When that main gear touched, there wasn't a damn thing you could do. That nose was going to be ugly, and you can see that in the film. Every time it comes in, it just slams down. The loads would, and the load would rebound from the nose back to the main gear as well. So there was a rebound load, the load of the airplane on the tail, and then every time you'd land, the nose would start to fall through, and instinctively you'd just pull back on the stick, just try and control it, even though you couldn't. And that would load the tail up, of course. The tail would be trailing edge up, and that would be an aerodynamic load in addition. So all those loads added up, and kind of like a deal like this. On a normal airplane, you got the gear pretty much close up to the CG, a little bit of a moment arm with the CG, but you got a nice long moment arm on the tail, and you can control it down. You know, the kid on the teeter-totter, you can let him down real nice and easy. The X-15, the fulcrum was right here. You were sitting right at the fulcrum, and so the kid on the teeter-totter was out here. He was going to fall through, and there wasn't a doggone thing to do about it other than load up the main gear, which resulted in failure of the gear on Jack McKay up in Mud Lake, and you'll see this in the film as well. We flew two separate kinds of profile, two different profiles, a speed or a heating profile, which was designed to study Mach number, shock effect on the airplane, aerodynamic or thermodynamic heating, and the stability and the controllability of the airplane had different Mach numbers. We'd get going Mach 5.5 or Mach 6, and if they wanted an increased angle of attack, you'd roll it over and pull it in at that Mach number so that you could keep the conditions the same, but change the angle of attack. And the number of flights like that. We'd launch at 45,000 feet from the B-52, hit the launch switch, get the engine going, control the airplane and roll, and get on an angle of attack of about 11 degrees, pull it up to 25 degrees or so for the heating flights, and immediately start a gentle pushover to level out around 100 to 110,000 feet, which was where most of those heating and high-speed flights were flown. Shut down at the energy condition that was called for that flight, and then glide on back in and set up a pattern to land at Edwards. Some of the more obvious things we learned about heating, where the nose, the leading edge of the wings had solid bar slots to absorb the heat of the leading edge. And then it took it Mach 6. And that bar worked okay, except it was cut into sections and made in sections for expansion. And in those sections, of course, the plasma, the hot air would get in those slots, find its way back to the wing, to the skin, and start getting some buckling. So they had to put deals over those slots, not a big thing. And of course, it's pretty damn obvious, you know, metal has different coefficient of expansion than silica does. And remember back in the 50s and stuff when the car rear windows, when they sit it out in the parking lot and let it get real hot, the back window would glaze over like that. It just kind of looked like it shattered little tiny pieces. That would happen. Sometimes we get a clean break, and because the stresses would build up on the corners of these square windows, and it would glaze over. It wasn't really a big deal because I'll show you in one of these films, in one of these things here, the windows were pretty small, but you were sitting right up next to them. They were about that high. But your head was right next to them. The canopy came down, it looked like that, and then it went around your shoulders. So your head was right up against the window. You had a pretty good field of view. Plus you could move that field of view. You know, it's just about moving the airplane around, maneuvering the airplane. So seeing out was not a problem. And landing would only have been a problem of course, this one has the right window is glazed over, so that means, well, I'm coming back in, I'm just set up for a left-hand pattern. I can see out the window for the pattern and hold the energy and land. If it was the other side, you'd set up a right-hand pattern. And you can't believe, and I got to admit, I wished, I didn't ever pray, but I really wished hard that I would get a flight where both windows would glaze over like that. Because what we got to do then, you had to jettison the canopy to see out to land. Of course, we had a full pressure suit on, with a visor and that fancy silver suit that was good out to Mach 3. So, God, you were safe sitting down there in the thing. But can you imagine how fun that would be? Come back from a Mach 6 flight, in an open canopy airplane. I got to admit, I got one of these silk scarves, and I'd stuff it in my flight suit pocket, because hoping that I'd have two windows glazed over, and I could slide down there in open cockpit. By the time the trucks would get there to get you out of the thing, you could have that scarf out and lay it. Never happened. We had several nose gear deployments. And the reason for that was that cable. Remember the cable I told you about that just attached to that T-handle, went back to the hooks? Well, that ran back inside the chine pretty close to the fuel tank, the ammonia and the liquid oxygen tank. So it kept cool during the flight. But the airplane would stretch 3.5 inches. And so imagine, a cable back there to the tail end, pulling real taut, and there's no place for it to go, so it just starts opening the hook. And that's what happened to Bob on several flights. The nose gear deployed on one flight line, scoop door came open, and another one of the main skids came down. So we had a placard made up for him. Every time Bob Rushworth would fly the airplane, we'd have this placard on the panel for him, reminding him not to extend the air. And the thing was, it was partly a rigging thing, but partly it was the airplane had been extended in length, modified and extended to go to the Mach 8. This was the number 2 airplane. And it had a deal on it. The landing gear, if you can imagine, this is the gear handle there at the panel. And this is the cable going down to the hooks. It had one of these compression springs like that to take up that expansion of the airplane. And I always thought it was just sloppy rigging. I never got to the simulator didn't have this in it because they just didn't have it in it. And you don't fly that airplane very often. And I remember on my first flight, I grabbed a hold of this thing and I pulled out a little bit. And I think, God, what a sloppy airplane this is. Well, this is all I was doing. I was pulling until it got to the end of that thing, and then you'd jerk and the gear would come down. And it was designed to do that. And so it just got well out of rig. And we had a few of those fun things. Some of the other heating things we learned, I'm going to go through this fast because I'm really kind of running out of time here. The airplane was modified to hopefully get to Mach 8 flight conditions so that it could take an engine, a scramjet engine out to Mach 8 conditions, see if it could sustain combustion. The Mach 8 dummy ramjet had a nose spike on it, and during the expansion program, Pete and I got it out to 6.7 Mach. A shock wave had formed and just homed in and made its home on this lower ventral fin, which was what held the engine, and it just burned right through the steel, Inconel steel. It burned right through, and Pete lost hydraulics and some electronics too, and you'll see that in the film as well. The other flight profile, beside the speed heating profile, was the altitude profile. And we would launch again at 45,000 feet, normally farther up range because it took more ground track to get back. They had less dynamic pressure and all that stuff. Same sort of thing, we'd come off the hooks, get the engine lit. You'd pull up to get a 45-degree pitch angle, or nearly that, depending on what the profile called for. And burn the engine until the burnout conditions that were planned for that flight. Normally about 150,000 feet for altitude flights, 140 to 150,000 feet. You're above the controllable atmosphere. The surfaces weren't really doing very much at that point in time, but you didn't know because one hand was on the throttle, the other was on that other stick over here, the aerodynamic stick. So you'd shut down, and first thing you realized was, hell, this isn't doing anything at all. So then you'd let go of it and start flying with the reaction control handle. And then coast ballistically up over the top, generally getting probably about 3 minutes of zero-G time. But during this coast time, you're essentially no dynamic pressure. And so the experiments that they had, we had a little experiment package right behind the canopy that the doors would open up, kind of like payload bay doors on a shuttle, but they weren't any bigger than this podium. And the experiments that were run on either star trackers or infrared ultraviolet signatures of the horizon, which we use for guidance control systems for the ICBMs. And what we would do is once the engine shut down, get the wings level, and then yaw to the correct sun angle that they wanted for the experiment, to get the data. Roll the airplane over to the horizon, and then sweep it through the horizon as you're going over the top. It sounded kind of spectacular, but you're so locked into one task at a time. Yaw to the right place, roll over 90 degrees. Got it. I'm there. Now sweep the thing back and forth. And normally it wouldn't take very long. It didn't seem like any time at all until it was time to close the doors, get the thing back ready for entry, and come in, start coming in, which we would do normally above 200.